small doubt, sir. So when we are doing the schematic, sir, so we were much precise on the width, sir, to be precise. So when we generated it, we got the we did generate, but we'll try it again using this. So when we generated it, we got the PS. I'm like PMOS and NMOS of different lengths. I'm like, okay, whenever I give the width as 7 or 8, and the width of NMOS as 4 or 5.
You are
So
using widths of 7 microns in your
yes, sir.
assignment?
Yes, sir.
Oh my God.
So
Do you
when we
really
use,
need that wide transistors?
sir, actually we didn't know how to cut the PMOS and NMOS into fingers. So literally I placed one below the other vertically by generating it, and that's how it happened, sir.
Sir, there is 20 femto load on the inverter.
Yes, sir, and 20 femto load.
Okay. 20 femto load के लिए आपको 7 micron बनाना पड़ रहा है.
Sir, and they were asking in 20 picoseconds, sir. I'm like,
Okay.
that was not possible by using NS. I'm like, okay, that was possible, but a bit hard to achieve in NSVTLP, but it was happening in NLVTLP. Yes, sir.
So what was your question, Vaishnav?
One second, sir. Actually, I forgot my question. Okay, yeah, I got it, sir. So whenever we were using the width, sir, I'm like, for suppose 7 and 4, we got different lengths of the PMOS and NMOS, sir. Sir, but now here, if we do it directly, then how would we mention? I'm like, measure the width of the PMOS and NMOS, because we are just running the poly over the active region, sir. So over there, width was predefined in the schematic, and then we went to the layout directly and we generated.
So over here, when you're making these rectangles, the active rectangles, you make this as width P and you make this as width N.
Okay, so we are supposed to measure that with a scale, and that's it, right, sir? I'm like,
Yeah. How else would you ensure the accuracy?
okay, sir.
So the length part would be but we had to basically ensure the length part would be when we are making without the P cells, the length part we have to be the channel length plus these poly to contact, and then that
No. Length, the length which you use, 60 nanometer or 65 nanometer or 80 nanometer, this is L, the width of the poly.
Yeah. And then I have to, for the minimum DRC, I will take that PO,
Yes.
PO to CO, and that will
Yes.
ensure the minimum area.
Yes. Minimum area would also have this minimum active to OD to N well spacing, and so many. See, all these will lead to rules, right?
Yes, sir.
Yeah. So actually, it's the first layout, so we are not aware all these rules. So that's why maybe.
So that is why I'm covering this in the class. Don't worry. Don't worry. You're not expected to know. आपने अगर refresher course में करा होगा या कभी पहले कर लिया होगा, that is one thing. Otherwise, you're not really expected to know all this. I know you've not done this earlier. Okay. So,
sir, I had one doubt. So suppose, for example, like earlier we were seeing the NAND structure, right? So for example, you made a shared, basically some area was shared, right? And to me, for example, what I'm looking at is that what area capacitance is basically getting transferred to the output. So I'm only focusing on that, right? So for example, if I say I'm considering an NMOS, say, for NMOS or PMOS, say, for example, and for example, right, we have a poly, right? Generally we draw one poly and then we have a one source string. Suppose we kind of to reduce that area, maybe to if we have a, for example, we sort of divide the poly sort of, and make a some kind of structure there, so that we have a drain in the common, and then we are connecting source with metal one, and then we are connecting to. So for example, so what exactly the factor I'm looking at here, I will be only looking at the diffusion capacitance area. See, only the thing I'm looking at is the diffusion should reduce, and then basically whatever appears at the load, that would be my driving factor only here.
So yeah, let me take you to that. This is actually, Raghav, what you're asking is, if I try to answer Vaishnav's question that, okay, I have 7 microns of PMOS and 5 microns of NMOS, and I have to draw them, how do I draw them? So abhi tak to possibly what you guys are doing is, you are saying that, okay, I will make one big PMOS over here. I will make one big NMOS over here, and I will make a poly between them. And this is how my thing would look. अभी तो आप ऐसा कर रहे हैं, है ना?
Yeah.
Whatever be
Yes,
the
sir.
width, you are
Yes,
saying
sir.
this is 7 microns, this is 5 microns, and I'm done with my inverter. But
Right,
that is not how library cell layouts are made. Come to think of
Okay.
it, I tell you, you have to make a wall. We are going back to the construction analogy. I want you to make a brick wall. And then I say that, okay, some bricks are this tall, some other brick is this tall, another brick is this tall, and then there is a brick which is this wide but that tall, and so on. So will you be able to make a good wall?
No, sir. No.
Mushkil hoga na?
Yeah.
So what is done is, we say that, okay, nothing of this sort doing. All the cells that you have to make, whether it is an inverter, whether it is a NAND gate, whether it is a NOR gate or an AY or whatever cells you are making, we will use a standard fixed height. Now what you can change is that if there is a small cell, you will use only this much width. But if it's a big cell, you will use much larger width. You're using the same area, but the height is fixed. Now what happens? Now you can actually place these tiles one over another and you can make a big wall. Am I right? Are you able to see this?
Yes, sir. So, but I have one thing to ask. So here, as when I'm drawing the layout, the height is not even in my control. So height is fixed.
As of now, I'm telling you, you will
Okay.
have to fix the height. Otherwise, how will you go about making this wall later?
But right now with the inverter, we are having, okay, because we are having 2 cells only. So that's why it is getting mad.
Because you did not even think कि आपको height constraint करनी है. If I tell you have to constrain the height, what will you do?
So, but that height parameter, I couldn't see that it was anywhere mentioned in the like.
It is not mentioned. It is not mentioned. But I'm telling you now.
So some way we can change the height. You're saying that.
So let me ask you, if I have to draw this 7 micron wala PMOS in a height of 1 micron, what will you do?
Sir, actually, I'm not able to get that height concept. That what exactly is meaning by this height than 1 micron? Are you meaning that the thickness of the gate oxide and the...
No. I am saying this vertical extent should be less than 1 micron. But my effective PMOS should be 7 microns wide.
I mean, so this extension is itself the width, right? So, I mean...
Cascade them, sir.
Sorry?
Like
place one by one each other in vertical, 1 micro, 1 micro, 1 micro, 7 times and connect them.
So what I can do is I will say that. So now let me go to, so this is how the layout view would look. Okay. Let's say that we will see itna sara layout banane mein, it takes a lot of time. Nahin? I have to make so many rectangles. So there's a different representation of layouts, which is called as stick diagrams. So you will find lots of details on stick diagrams in your West Day also. Okay. So what do? We say that, okay, there is one PMOS. So this horizontal line represents what we call as active region of, let us say, maximum 1 micron width. Can we say this? Can we say this, that this horizontal line represents active region, this kind of a rectangle, which is 1 micron wide? Can I make this assumption?
So you're taking the width to be 1 micron, right?
Yeah, but I'm showing it, representing it only as one line. I'm not making it into a rectangle. Over here, I made this rectangle to represent the active region. No?
Right.
Over here, I'm saying I'm just using a line. I'm just using a stick. Can I do that?
Okay, so you're not representing the length basically of channel.
I'm just representing
the width.
The width of the active region. I'm not even talking about poly yet. Channel की बात नहीं आई अभी. अभी तो खाली active की बात आई. I'm not using rectangles. I'm just using sticks. That is
Okay.
why it is called a stick diagram. Similarly, I use sticks for the poly also. So let me say that this represents poly, this rectangle, the rectangle that we have made over here, that is represented by one stick over here, vertical stick, red one in color. Can I say this?
Yes.
Let me say contacts I am representing by such crosses. Can I say this?
Yes, sir.
Yes, sir.
Now, if I have to make a PMOS which is 7 microns wide, what do? I say that, okay, I have just 1 micron width available to me. To make a 7 micron device, I will put 7 PMOSs in parallel. And what does parallel mean? Parallel means that I will have to short.
We'll short all the drains together and
Not all the planes. So I will now short, let us say, sorry, and this, and I will short the other like this.
So that black one is also metal, right?
Black one is also metal. I'll just use VDD for black. And what else do I need to short? I need to also short the polys. तभी तो gate connect होगा. Are you able to see this?
So it's a bit confusing, sir. I mean, so why you have two sets of metal? Like one is black and why can't be a single one? I'm not able to get.
No, I just used the black one because it was available readily there. I can make it blue. Don't worry. Let me make it blue.
I mean, so why not connecting all the 8 contacts with a single like metal kind of running? Like you're missing 2 sets, right?
Okay, you tell me. You should have the answer for this. You don't need to
sir,
ask me.
we are connecting the drains together and source together, right, sir? In this.
Yeah, if I connect all 8 of them together, then all the sources
Dead
and
short.
drains will be shorted.
Yes.
Yeah. Okay.
Okay. So what do I need to do to make 2 devices in parallel? I need to short their gates and the source and the drains. There are 3 nodes that I need to short. Am I right?
Yes, sir.
That is what I'm doing. 1, 2, and 3. So now, whatever device size, whether you want to make 7 microns or 10 microns or whatever, can you make it within the height of, let us say, a total height of 1.5 microns or something? Let us say, whatever. Can you make it?
Yes, sir.
So this process is called as splitting into fingers.
Sir,
Yes.
sir, using this parallel, dividing it into fingers, won't this increase the area?
Yes, but what were you constrained about? You have to build a wall.
Yes, sir. Sir, actually, I tried a similar thing. I was able to meet the specification in smaller widths, but then I thought of area, then I skipped this idea.
No,
I
but
thought I will
you have to do it like this. You have to fix the height. So how do you fix the height? अभी तो मैंने आपको कुछ भी height बोल दिया. How do I arrive at a height? How much height do I need for these cells? Vaishnav, you have a question? Your hand is raised.
Sorry, sir.
Okay. So
Sir,
how do we raise?
sir?
How do we fix the height?
So this height, I'm not able to visualize it. So for example, this width itself, the height we are talking about, the width itself.
No, See, height is okay. Let us look at it
Can you
like this.
help me visualize it, because I'm not able to
Yeah.
get what exactly you meaning by height.
Sir,
Let's go.
height by number of PMOS or NMOS we want, so that we can fix the height of each PMOS. Smaller.
So let us go back to this layout जो हमने पहले बनाया था. I want to find the height of this cell. How would I calculate it? I will say there is active to n-well, OD to n-well spacing, plus, let us say this is WP, plus OD to n-well. Then plus OD to the n-well to OD,
Yeah, right.
plus width of NMOS.
Yeah, and then
extension of poly. And then if I have to consider that I have to make walls, then this cell would come above another cell. Are you able to see this?
so this hole is a one cell, this whole NAND gate.
Yeah, this would be one cell. There would be another cell that would come beneath it. So I have to ensure this poly to poly spacing is also taken care of.
Okay.
So I will do PO to PO by 2. Why? Why by 2?
The minimum spacing is we have to ensure, right?
Yeah, because if I leave half DRC here, half DRC in the other cell, overall full DRC will be met.
Yeah. So the other PO is of the another cell you're talking about now,
Yes.
the next cell. Okay.
Yes.
Okay.
So what has happened now? Now this is what is my height.
So won't the PTAP and that via that also come into picture here? Because in layout we were
Very
making
smart. Very smart. So you're taking me further ahead in the session. Great. So now look at it like this. Why do we need PTAPs and NTAPs?
Yeah, that was not clear even yesterday. I asked in the office also. So I mean, because it was we have actually in the virtuoso layout like the GUI we are calling it as a via. But I was able to relate it why we are calling it a via. I mean, it doesn't appears to me like we are creating some via or that.
No, it's not about via. My question is, why do we need NTAP and PTAP? So I see Madhur and Gagandeep, you have raised your hands. Madhur, you have a question?
Yes, sir. I have a question on the stick diagram. Yes, sir. Yeah, so can you show the stick diagram?
Yeah.
So this above stick, the top stick, this is one entire drain region for different.
This is one active region, which gets split into source and drain depending on where the poly is.
Okay, sir. So wouldn't source and drain? I mean the source. Or let us call the first source and drain for transistor 1 and the next source and drain for.
Yeah, वही करा ना. देखो, I put S over here. This is the source. This is the drain.
Yes.
Then for this part, because drain is shared. So this is the drain. Then that becomes the source. Okay, now source is shared. So for the other thing, the other part becomes a drain. So that is why we connected alternate contacts, alternate active regions. We connected through metals to get source and drain nodes. So this node is drain node, and this node is source node, and this node is gate.
Okay, sir. And sir, how are two source and drains, adjacent source and drains being isolated from each other? You tell me.
Let us draw the horizontal or the cross section view. So what will we find there? We will wait. Let us PMOS side का ही बना रहे हैं. एक मिनट रुको. Just give me a minute. So let us draw the cross section. Let us say this is the silicon surface. Let us say हम इसके पॉली को बनाना शुरू करते हैं. 1 poly, 2nd poly, 3rd poly, 4th poly, and so on. So what is happening in this source and drain region? You are getting this diffusion. first diffusion, second diffusion, third diffusion, fourth diffusion, fifth diffusion. Then what did you do? You made metals and you connected this one with this and this. And through another set of metals, you connected this. Let me just, and this, and you would go here. So is there a way that source and drain would get shorted amongst each other?
No, sir.
Hai? So you just look at the cross section, it cannot happen. Source and drain are separated from each other through the depletion region.
Okay, sir. Got it, sir. Thank you.